Hello, everyone. It's a great pleasure to welcome you here today, those of you in the room or the much more many of you who are online, for our second scientific meeting organized both by the Veolia Institute and the Department of Scientific Expertise and Technological Expertise. The goal of these meetings is to promote and make accessible scientific knowledge on environmental health and public health. Of course, it's important because this directly contributes to improving public health, and it's particularly important for us at Veolia because every time we work on drinking water, on hygiene, on wastewater, also on eliminating air pollution, we directly and indirectly contribute to public health. So it's to better know relationships between the environment and public health that we organize these meetings with very high-level experts, and we thank them very warmly, who come to share their expertise and experiences with us and to give us the latest breakthroughs in science. We recently had Professor Yves Lévy, who talked about the impact of chemical pollutants on human and environmental health. Today we have the honor and the pleasure to have Marie-Cécile Ploy and Christophe Dagot, who will explain in just a minute about resistance to antibiotics. So please make the most of these exchanges. We will have a Q&A session after the presentation by Marie-Cécile Ploy and Christophe Dagot, and then we will have a cocktail lunch that you are all invited to, and you can continue your conversations then. So I would like to thank Philippe Sébrac and the entire desk to have helped us organize these meetings, and I will give him the floor to say more about our two guest speakers. Thank you very much, Nicolas. So antimicrobial resistance, well, what is it? This is a phenomenon, and we've been seeing signs of this for years. And so this is the proliferation of genes which allow resistance to antibiotics. It's not something that most people are aware of yet among operators. And so it's our role within DEST to try to look to the future. So we've been working in this for about 5 years. We've been keeping watch and we've been interacting with the scientific community, especially the Science Academy and University of Limoges, who are carrying out research on the ground to better understand the extent of this phenomenon. So what we'll be talking about this morning is whether it's serious, what we know about antibiotic resistance, are we concerned, and what can we do collectively and individually. And today we have the great good fortune to have two eminent experts who are recognized at world level on this matter. So Marie-Cécile Ploy, who is professor of microbiology at the University of Limoges, a PhD in pharmacy, and she's the head of the bacteria, virus, and antibiotic resistance research stream, and professor of Limoges in charge of the ecological transition for sustainable development at NCIL-NC, you're all familiar with, in Liège, and he's head of the resistance and environment work stream at the ResinFit laboratory. And as a moderator, we have Charlotte Arnal, who is the desk expert and our referent on antimicrobial resistance. And I will now give the floor to Charlotte and our guests to jump right in. Thank you, Nicolas, and thank you, Philippe, for your introduction. Hello, everyone. As an expert in microbiology and the environment, I have the pleasure to be moderating our V-Talks today with our very distinguished guests, Marie-Cécile Ploy and Christophe Dagot, who are both specialists on this topic. And so I will be the spokesperson for all of the questions that we all have about antimicrobial resistance. Antibiotics, we all know what those are. We've all taken them at least once in our lives, whether penicillin, maxicillin, or retrimacin. These are medicines which have allowed us to considerably reduce fatalities caused by microbial illnesses since they were invented in the 20th century. Unfortunately, today, the flip side of this is that their massive use and their repeated use makes them less effective over time and can lead to antibiotic resistance, which could prevent us from treating common diseases tomorrow. So it will be a public health issue. Right now, there are about 1 million deaths every year because of antibiotic resistance, to the extent that the WHO in 2015 declared that it was one of the 10 most serious threats for humanity. And in addition to being a threat for public health, it's also a problem for the environment, because antibiotics that we consume are then found in wastewater and enter into the water cycle. We will have all understood that we are all impacted by this, individually and collectively, and as well as through what we do as water operators and waste treatment professionals. So for our meeting here, Marie-Cécile, could you define what antimicrobial resistance is? Because we hear more and more about it. So maybe we could show the slides. So antimicrobial resistance. Well, first of all, you have to realize that this is a natural phenomenon. Bacteria naturally resist antibiotics because most antibiotics are synthesized using bacteria or fungi from the soil. And then those same bacteria can't be killed by their own production, and they have resistance mechanisms. And then in the soil ecosystem, there are bacteria that have resistance. So it's perfectly natural. But why it's getting worse and why it's a public health issue is that taking antibiotics, which is very good in and of itself because they save millions of lives every day, but taking antibiotics, as you can see here, this is what we call the selection pressure. And in fact, and what you see here on this slide in the yellow is the bacteria which are resistant, and then in red, the resistant bacteria. So you can see they're very few. But if you do nothing, then there's no reason for this balance to be modified. But then, if you have a pressure on the selection because of what you're trying to kill, then a resistance will increase and can then be turned into the main resistance. And this is how you get bacteria through selection, through natural selection. And it's not just antibiotics that add to this pressure. So could you explain the link between these antibiotics and antimicrobials more generally and these this antimicrobial resistance? Well, there's a direct link. It's complex, but it's still a direct link, which you have here on the screen. At the bottom, this is consumption of penicillin in a variety of countries, so with the quantities. And then on the y-axis, it's the pneumococci. And we all have some of these in our throats, and this can lead to serious infections. So then you have the percentage of pneumococci which are resistant to penicillin. And you can see that there's a direct correlation between consumption and resistance. And then there's France at the top. So this was in the 2000s. And since things have improved, but we can see that countries with a low consumption of penicillin also have a low level of resistant bacteria. So there's a direct link. Thank you. So are we the only ones impacted by this? No, humans aren't the only ones impacted. There's something that, well, for a very long time, what we have at the top of this was that it only concerned humans and only hospitals. For us, so outside of hospitals, everything was fine. But in France, over 90% of antibiotics are prescribed in cities, contrary to the Netherlands, for example, where 90% of antibiotics are prescribed in the hospital. But it's not the same country, not the same structure. And then, so we thought, okay, it's only a problem in hospitals. And then, or no, it's only a problem in cities, or only in retirement homes, in nursing homes. And then, and so just looking at humans, there's also people who travel. Very awful. Well, when I ask my students whether they've never taken the plane in their lives. 20 years ago, it would have been 40 out of 50 people would have raised their hands. Today, it's one person. So people travel much more broadly. And of course, when you travel, you transmit and you get bacteria. And you can pick up resistance this way. And then we started looking at animals, especially livestock, and more recently, domestic animals and the role they play, and then wildlife that live around us. Rats, lizards, hedgehogs, etc. And then since the beginning of the 2000s, maybe a little bit more, we started looking at wastewater and the role of the environment. And this is why this is really a One Health issue, requiring a One Health approach. So it's always simpler to say it's somebody else's fault. So you're talking about physicians. They'll say, oh, well, no, it's all very complicated if you look at what's happening in animal health and veterinary health, but then you speak with vets or livestock raisers. They no, it's not a problem for us. You have to look at what's going on with the doctors. It makes no sense because you don't get anywhere with that. It's really an overall issue, but of course it does concern animals. But looking in terms of a biomass, there's more consumption of antibiotics amongst humans than amongst animals. However, in the veterinary world and the world of animals have made the issue their own. And we see here with the figures, the very high figures in terms of how much they've reduced consumption of antibiotics with a very strong effect, so at the bottom of the slide. So a direct effect also on the number of resistance genes amongst reproductive animals. With pets, it's a little bit more complicated, and you can see that the decrease was only of 3% amongst domestic animals. Thank you. So Philippe, in his introduction, mentioned emerging topics or emerging pollutants. So emergent is often used for new issues or new pollutants. Are antibiotics new, actually? Well, no. As I said earlier, antibiotic resistance is a natural phenomenon. And here are 3 studies. The one on the left carried out by colleagues from Canada on the permafrost. So they drilled down and they took out carrots very cleanly to avoid all contamination, and through genomic methods, they found antibiotic resistance genes. And of course, they didn't have antibiotics back then. The first antibiotics were first used during the Second World War. And then this is an Aztec mummy. And they found, well, antibiotic resistance. And then the third, it was a cave that had been closed to the public, so no contamination from the outside. And here too, there was a presence of resistance genes, and so antibiotic resistance genes. So emerging phenomenon, well, there is debate around this because emerging, people think that it's something new, but it's actually what's emerging is in human and animal health, is that it's becoming a public health issue because people are discovering little by little that most of the antibiotic resistance genes in bacteria which are of concern, well, their progenitors, so their ancestors, come from bacteria in the environment. So here you have a great example of a resistance gene, which is CTXM, which provides a lot of resistance to a lot of molecules. And that gene at the bottom, over the evolution of the bacteria, it is taken up by a variety of genetic elements, which are mobile, all the way up to the large blue bacteria, where they enter the plasmid, and then the E. coli, which is found in our guts, can eliminate it in our feces, and therefore it's found in wastewater. And then when you have this gene with a mobile genetic element in the right bacteria, well, then it spreads. And now there's worldwide spread over the past 20 years of E. coli and the CTXM. So it's just like Russian dolls. So gene in environment in a bacteria. Thank you. So if I've understood correctly, the bacteria become resistant and acquire superpowers, basically. Does this mean that we will no longer be able to treat common illnesses tomorrow? And are we only concerned if you take antibiotics? No, unfortunately. Are there infections we will no longer be able to treat? It's not the case so far in France, even though in some cases it's complicated. But in other countries, where the prevalence of resistance is much higher, then it can become very difficult to treat. So if you get an infection and you are hospitalized in some countries, there are many risks of being infected by a highly resistant bacteria, and then no treatment will be possible. So why is this less common in France? Well, we have a very clear policy for the prevention of infectious risks, often called basic hygiene, but that's very reductive. There are resistant bacteria, and they're transmitted. So we shouldn't only focus on reducing consumption of antibiotics. We also have to focus on transmission. If we don't try to work on both at the same time, we won't get anywhere. Here you have examples of transmission. If you sneeze without, and we all know this since COVID, so if you sneeze without putting your mouth into your elbow, then you can see the spray that you emit, which can get very far. And if you have resistant bacteria in your throat, or even non-resistant bacteria, and then traveling as well, and Christophe maybe will give an example later, and then the best transmission is from hand to hand. So in hospitals, anybody who's in contact through their hands, who has to touch equipment, for example, you would be amazed at the number of people who do not wash their hands before leaving the toilets. That would seem like basic hygiene, but it's not necessarily respected. Okay, thank you. Could you maybe illustrate now how this translates on world health and on health of the French? There have been studies. The European Agency for Transmittable Diseases, for Communicable Diseases. This is an agency of the European Commission, and every year they carry out studies. They have a network which is called EARSnet, which looks at consumption of antibiotics and resistance among. So you have the maps here, and you can also visit their website, ECDC, and there'll be a lot of interactive maps. And at the left, this is Klebsiella pneumoniae, which resists the cephalosporins of third generation, which are broad-spectrum antibiotics which are used for severe infections. And the redder it is, the higher the prevalence. And you can see, like I was saying earlier, we don't have the same levels of resistance from Norway, for example, and Greece, which is dark red. and the same to the right for multi-resistance of several families of antibiotics. And now in terms of world health, as you said earlier, this diagram comes from a publication that appeared in The Lancet a few years ago on the impact of antibiotic resistance on health and mortality around the world. It's over 1 million deaths every year around the world. And to the left, you can see the impact of antibiotic resistance. So it's 1.3 direct deaths due to antibiotic resistance and several million deaths associated to resistance to antibiotics. And unfortunately, to the left of the diagram, these are the poorest countries, the most vulnerable countries, where unfortunately health conditions do not make it possible to prevent transmission. It's true that in Europe it's high, but it's equal to the weight in terms of mortality, the combined weight of the flu, AIDS, and tuberculosis, just in Europe. And 3/4 of the AMR burden is linked to hospital-acquired infections in Europe, which is why, so it's important to take into account the fact that these bacteria are being transmitted. We cannot solve the problem of AMR if we don't solve the problem of transmission at a variety of different levels. Christophe will go more into environmental aspects later. And then the burden of HAI represents twice the burden of 31 other infectious diseases, 2.6 annual cases, which is to say 91,000 deaths. So it's 2.6 per 1 million inhabitants. So people don't realize, maybe in the general public, because it's rarely said that, oh, well, my neighbor died because of antimicrobial resistance. You'd say, no, he died of pneumonia or died of a serious infection, but not, he died of AMR. And so people don't make the association. I mean, but AIDS, diabetes, high blood pressure, people don't realize that it's actually due to antimicrobial resistance. So that's what makes it hard to take into account. Thank you. So yes, we see that antimicrobial resistance is an important public health issue and that it could have different impacts in different areas of around the world. But does this mean that it's regulated? Actually, no. Well, in human and animal health, no. So we've talked about the deaths, and here are some predictions for 2025 in human deaths. So linked to antimicrobial resistance, because we often see AMR in English, and we talk about antibiotics, but actually antimicrobials is antibiotics, antivirals, antifungals, and antiparasitics. So this prediction for 2025, you can see the weight, which is completely different depending on the country. It's much higher in lower income countries. And then you have examples on the left of getting access to clean water and then transmitting the antibiotic resistance genes. And so there are also resistances at world level. The WHO has a program called GLASS, and you can see the figures for the resistance, but there is no regulatory, it's not mandatory in Europe or in the world to monitor antimicrobial resistance. Okay, thank you. And do we have an idea of the economic impact of AMR? Well, the OECD for Europe does carry out studies on this topic, and it's publicly accessible online. I listened to a conference they had online, and in September there's going to be the General Assembly of the UN in New York. And there's a high-level meeting on antimicrobial resistance. At political level, they're having a whole bunch of preparatory meetings for a declaration of antimicrobial resistance at the General Assembly of the United Nations. So there's a meeting last week about the various stakeholders. And there was somebody from the United Nations, from the Food and Agriculture Organization, and said, well, no, for politicians, you have to give us figures to be able, so that we can know what the impact is. We won't be able to defend legislation or anything. We don't have any of these figures. So that's why these OECD reports are so important. And in this report, it says, so there are reserve antibiotics where there's already a lot of resistance, and they've been modeling an increase of 45% by 2035. And that higher health expenditure and reduced workforce productivity for Europe costs 11.7 billion euros per year, and that extra days in hospitals. So say you come into the hospital for peritonitis, you are operated on, you spend a few days in the hospital, but if you get a hospital-acquired infection with multi-resistance, then this will increase the length of your stay in the hospital, which comes at a cost for society. And so this represents, so the extra days in the hospitals will represent, so this is in Europe, so 9.5 million euros in Europe. So that's not negligible. Thank you, Marie-Cécile. And we're now coming to the influence of other factors. So climate change, for example, is this an external factor which can accelerate or worsen the phenomenon of resistance? Yes, and there are a lot of analogies between the two, because climate change and antimicrobial resistance will have an impact in the long term. And it's not necessarily visible, even though climate change was making it much more visible. But AMR, we have to find means to make it more visible.
When it comes to climate change, we tend to believe that it's up to someone else to make the effort of fighting it, but there are lots of publications on the topic, and according to WHO, climate change is indeed the highest risk for humanity. 250,000 additional deaths are expected every year between 2030 and 2050. We see this in France as well. I mean, tiger mosquitoes are everywhere, and not just in the south of France. They're migrating north. I saw the maps just last week, and they can be found as high as north as Pas-de-Calais in the north of France. And also diseases such as chikungunya and dengue fever. A lot of unpleasant diseases are being developed because the weather's getting warmer, and this promotes the transmission of infectious diseases, which have been described as being increased, worsened by climate change. So we're talking torrential rains. This will destroy the soil. And climate change causes weather refugees with massive influxes of people into urban areas which are not designed to host that many people. And promiscuity in proximity means transmission of diseases, and also there are ecosystem-related changes. I said that antibiotics are developed in the environment, and bacteria exchange genes. Not only can bacteria be exchanged from one person to another, but you can also transmit mobile genetic elements of E. coli, for example, in my bedroom back at home, and then my friend in a hospital will have Klebsiella pneumoniae, and with the same level of resistance, it may not look like it's the same, but the mobile genetic element has jumped. The barrier has jumped from my E. coli to his Klebsiella pneumoniae. So it's been shown that increase in temperature actually increases those horizontal gene transfers. And microbial communities in the soil, in the environment, or ecosystems with their own balance, their own homeostasis. And so there are ecotoxicological impacts of antimicrobials on the environment. And then let's not forget the biocides. And because this has an impact on the GI tract, when you take antibiotics, and that is how we generate resistance, the selective pressure effect I talked about, that's done in the GI tract, because we have as many bacteria in our body as there are human cells, and this will have an impact on the soil microbiome and completely, radically change the ecosystems. But those ecosystems are tied to plant health and geochemical cycles, and of course this has an impact on microbial biodiversity, which goes down when there are antimicrobials in the environment. And those changes in biodiversity will also cause less diversity in terms of microorganisms. And because microorganisms are a source of antibiotics, and this means that we're less likely to discover new antibiotics in the future. Thank you, Marie-Cécile, for all of this information. Now, regarding part one, this is what I take home. ATB resistance is a public health problem which is gaining ground. It's a problem that spans several areas of activity, animal and human health, of course, but also ecosystem health. And because it is a complex issue, this is why we need a One Health approach, and we need to coordinate between the different areas of business so we can resolve the problem. Now, talking about human activities, Christophe, could you please give us additional information regarding those activities that are the highest contributors to AMR? And what are the sources of ATB resistance? Now, I agree with you. I joined Marie-Cécile's team 10 years ago to work on the environmental front. Initially, her laboratory focused on medical issues, and I came from an environmentally driven lab, so we decided to pool our expertise so we could develop a more holistic approach. Now, if we look at this world map, in red you have those areas where contamination is rife. So 90% of those transmissions take place in hospitals, either contamination by hand or when you seize and you spray and contaminate people around you. And everything ends up in the environment. When you take drugs and you pee, and the drug ends up in the wastewater, and the wastewater ends up in the environment, and in wastewater processing plants as well. So different routes of dissemination. It all starts with animal and human use, and then it all finds its way into the environment. So we know that this made headlines, but we found that at a global level, pretty much every river is polluted by ATBs at varying degrees, or micrograms or picograms or micrograms per liter. It all depends. And this obviously has a selective pressure impact on indigenous bacteria. Now, we talked about E. coli, which is found in poop, and the poop finds itself in wastewater and therefore in rivers, and you mix it up with the selective pressure impact. So you have a very successful recipe for AMR. Now, the different spots that are described here, there's one that's easily identifiable. Hospitals, that's where people take the most antibiotics, so that's where you find the most ARGs. And then you have wastewater processing stations, which collect all urban effluents. And then you have industrial activities. Let's not forget about industry. They are underrepresented on the map, but antibiotics are produced abroad. Remember the mortality maps? Well, the highest concentrations of antibiotics are found in China and India, where ATBs are being produced. So this generates resistance, and those bacteria that are created in China and India are going to get on the plane. And eventually, bearing in mind jet lag, and the time difference, they will find themselves in our rivers. Now, the food chain as well. What gets into the food chain? Well, pesticides, all of the plant health protection organisms generate AMR and therefore selective pressure on environmental bacteria. And then it all finds itself in the water and the soil. And this causes changes in ecosystems. On the right-hand side, you see the tree. That's a balanced ecosystem with bacteria that maintain themselves, and there are laws that regulate that balance, and natural antibiotics are produced. And then you have human presence, what we call anthropization, and this causes the dissemination pretty much everywhere of ARGs, anti-resistance genes. So you have these so-called natural environments, even though that's hard to define, and then you have more urban environments. Thank you, Christophe. So based on what you're saying, I understand that Veolia has different businesses, whether municipal contracts or industrial contracts, and also reuse of waters, and also the use of sludge as manure, as fertilizer. This leads me to a hot topic. Here's an important question. Wastewater treatment plants, could they be critical hotspots when it comes to AMR? Do we know what role they play in the development and dissemination of ATB resistance? Oh, definitely. By definition, Veolia is concerned and involved if we're talking about water pollution. So we need to find what a hotspot is. Well, 3 factors converge. And you can see them on the screen. This was produced by ANSES in 2020. So you have a selective pressure effect that causes the development of those MDR bacteria. But this is manifold. We're talking antibiotics, but other molecules, other products as well. So, of course, you need ARGs in order to ensure the transfer. And what you see at the bottom is what we call horizontal transfer of genes between bacteria. That's what Marie-Cécile talked about, how genes can be borrowed between bacteria. And then you have pathogenic species, which threaten human health. You may have exchanges of ARGs without any health risks, but the recipient bacteria must be a pathogenic bacteria in order to infect you, contaminate you. So in this representation, it's a pool, it's a reservoir, like a huge library of genes, and you have lots of ARGs. In order for them to be active in your body, they need to be transferred to a pathogenic bacteria for animals. So on the right-hand side, what do you see? This is often considered as a hotspot, but basically it's the recipient of everything you produce in the city. So hospitals, vet practices, veterinary practices, etc. So wastewater treatment plants process nitrogen, phosphorus, etc., and a bunch of other molecules. So see the pie chart at the bottom? You have in effluents, you find so-called normal bacteria in blue, and then you have bacteria that carry ARGs in red. And so the biological treatment process begins. What happens? Here we're talking grams of bacteria, grams per liter. So it's a different scale altogether. And you see there's an increase in bacterial concentrations, so hypothetically, an increase in the concentration of MD or ARGs. So now, we're talking about water here being processed, not sludges. So statistically, you're going to reduce through that biological processing the concentration of bacteria, but the bacteria that are generated at the end of the chain, are they not more resistant than those that came in? That's a big question. And that's a concern we have. In treatment plant, because it's a petri dish basically, isn't there that we find the most transfers between indigenous water processing bacteria and bacteria coming out of hospitals? So yes, maybe there are process-related parameters that we need to look at. So plus more or less oxygen may have an impact on the increase in pathogenic bacteria. So if I increase oxygen, does it get worse or better, etc.? The older the sludge, the more you have specific bacteria that grow, etc., etc. And of course, you need to look at the process. So it's really up to you. It's up to Veolia to propose processes that are based on membranes, for example, or even treatments that are much more intrusive, such as disinfection. So there are technical solutions available to ease our concerns. Now, I don't have much time to talk about that, but there are concerns that haven't been resolved when it comes to what happens in a wastewater processing plant. There are potentially genetic transfers that are taking place. I'd like to remind you that at the end of the day, we need a pathogenic bacteria in order to create a health risk. Thank you, Christophe. Earlier, I put a question to Marie-Cécile. I asked whether ATB resistance, whether AMR is something that's regulated. And I think that in the future directive, when it comes to processing of wastewater, there are plans to monitor AMR. Could you tell us more about that? And also, could you please explain why it's so important to measure how effective and efficient our sanitation processes are? Yeah. Oh, we talk about that every week, and we wonder what's different now relative to last week. Yeah, so this was enacted. It still needs to go through the European Council, but obviously the elections may have an impact on the timetable for managing this. So let me answer your question regarding ATBs and ATB resistance. The directive is about surveillance, it's about monitoring. So lawmakers want us to monitor the situation. So that means we don't really know what to do with the results, but at least we know that it's important because there's a risk for human health. So we will monitor the situation. The question is, where do we do the surveillance? Why do we look at the wastewater treatment plant as opposed to the rivers? Better, maybe we should do both. So lawmakers believe that effectiveness of treatment plants must be validated. It's an important point. It's not just about environmental contamination and health risk. It's whether or not we're able to manage that risk. Maybe additional measures are necessary in order to manage that risk. So the problem is that this directive doesn't provide much information. Charlotte and I were talking, and we were wondering, when should we make the measurements? Before or after? Okay, that's been resolved, but when, what time of year, what season should we do the measurements in? That's important, and why not do it in hospitals as well? Because it's a hotspot after all, so why not take measurements in hospital hotspots? So we've got answers to those questions. One thing is certain, however, lawmakers have included this in the legislation because they realize it's important not to increase the environmental pool or reservoir of MDR bacteria. What about ATBs? Well, that's a little simpler. Now, when I talk about ATB treatment, I'm talking within the treatment plant. We've been using this for 20 years, and we know that some bacteria are easier to eliminate than others. We need to look at that selective pressure effect. There are factors that can increase selective pressure. So ATBs, heavy metals, and all of the other molecules that can increase selective pressure. So it's not just antibiotics that we need to target. It's general pollution. General pollution by emerging organisms. Okay, thank you. So some uncertainties remain relative to the new directive that's going to come into place soon. In your opinion, what about the parameters that we need to monitor? What are the best indicators for monitoring ATB resistance? We've been asking ourselves that question for 15 years. We're always looking for the best indicator. as an operator, what is the best indicator of the level of ATB resistance in a given environment? I'm sure you understand that AMR is not as easily measurable as a simple molecule because, well, you have a concentration plus an effect plus a transfer plus a whole dynamic, so it's a little more complicated. But there are avenues we can explore. So WHO has proposed a definition, a method. Okay, just so you know, there are two general methods for measuring purposes. So there are bacteria that you can cultivate in a petri dish. And then we have genomic methods where we measure genes. So WHO has proposed this method. And it refers to the three media: men, animals, and the environment. So like a tricycle. And it's a relatively simple medium, agar, and you can measure E. coli bacteria. That's the bacteria that goes through the GI tract and that we excrete through poop. And when they are resistant, they carry large spectrum, extended spectrum beta-lactamases, ESBLs for short. So we're going to define this method. And the main upside, according to WHO, that this method is simple, affordable, and it works for all three media. You find it in animals, in humans, and in the environment. So the idea is to create a general indicator for all three media. It's simple, it's affordable, and it can help you determine public health policies in France, in Western countries, and in emerging countries as well. So, like I said, it's simple, it's affordable, and any local lab deep down in Asia or Africa can implement it. So that's the idea, and it's been accepted. The third or fourth point, that method has been standardized, and this means that all labs across the world will use the same method. That way you can compare things that are comparable. What can be done in France can also be done in Africa or Egypt or Asia. But again, it's only ESBLs that are used as indicators. So you need to grow the bacteria. Here's another method, however. It's more complex to implement, genomic or metagenomic methods. I'm now going to give you a class in genetics, but we measure a gene, a bit of gene. Okay, and we open it in all resistant bacteria, and we measure its concentration in various media. So here's an example. So one gene out of the billions we have, we measure one gene out of the billions we have in our body, and we look at what happens. Now, this has been going on for 10, 15 years. The first genes we had, it was an exploratory method, but we looked at European communities. 15 years ago, we compared effluents discharged by hospitals, discharged by cities, discharged by farms into rivers, and also we measured this indicator in the drinking water at the end of the chain. So you have high concentrations in care centers and lower concentrations in urban centers, in agriculture, or in urban water. So we have an indicator. We don't really know what it indicates. There's a certain level of resistance, but we don't know what bacteria we're talking about. We don't know what ARGs we're talking about or which drugs they're resistant to. So it's an indicator about a level of pollution, but it's not very detailed. So we needed to go further. You can measure 10, 20, 40, 100 genes and target specific diseases. So that's one indicator. So let's see how it moves around on the map. To make things more exotic, I decided to show you a map of Guadeloupe. So we looked at the different catchment areas in Guadeloupe, whether or not they're touristy areas, whether or not they're impacted. So, and we looked at ARGs, 15 families or so of ARGs, and to look at what happens between the two sides of the treatment plant, upstream and downstream. So we measured concentrations in feces from lizards or cows and other animals. And the second thing we looked at is tourists. Do they provide specific ARGs? Do they bring specific ARGs? So we made measurements in planes as well. So this means we can measure the effectiveness of wastewater treatment plants in Guadeloupe. Do they work? Are they able to reduce ATB resistance or not? And can they help reduce the level of ATB resistance and associated factors such as heavy metals? So I won't give you the results. You can read the publications when they come out. But typically, this is a good indicator for monitoring what happens in a catchment area. And then, potentially, you can measure pretty much every gene. And this is we move into metagenomics. We try to understand the mechanism rather than the indication for the source of pollution. Okay, let me wrap up on the idea of indicators. It's a complicated idea. Every time there's a new research program, a new EU research program, the idea is which relevant indicator should we choose? You can choose whatever you want. For Veolia, for example, you can look at the effectiveness of the wastewater treatment plant. Does it work better with membrane technology? Maybe other technologies are sufficient. If you want to go further and define health risks, maybe you need to dig deeper. If you want to understand the mechanism, maybe you need to work on plasmids and bacteria, etc., etc. So this whole idea of indicators is a little complex, but we manage. Now, during meetings, now what's being said is that it's no longer a question. We can use those indicators to address the problem. At the moment, there's an EU program called AONET. It'll work on a dozen indicators chosen by our French network, which has selected 3 to 5 ARGs. So actually 3 ARGs and 2 indicators, and they're trying to standardize that, have that standardized by FNOR via the AONET program. And AONET added 5 more ARGs, anti-resistant genes, to try to achieve EU validation so that operators have something to measure. Something that's robust and reliable in terms of analytics. Thank you, Christophe. Now, based on everything you just said, clearly there's a wide variety of potential indicators in terms of potential research avenues. I have a question regarding those indicators. Is that standard lab work? Is that done routinely? No. Yes. Some of them are easy to do, and all bacteriological labs can do that. You can actually grow the cells in petri dishes, but genomics is a little more complex. I mean, quantitative PCR is technology. Isn't that complicated if you're dealing with one gene? But in terms of metagenomics, things get more complex. Not every lab can do it, has the capabilities to do it. If it's easy enough with a single bacterium. Now, we talked about Ecolab. It's mostly for health policy purposes, but what we're doing now, and we're doing routinely, we use labs to monitor the situation, and Veolia does it as well, to some extent. Yeah, we dabble. Thank you, Christophe. Now we have a better idea of how this works. Let's move on to the solutions. Marie-Cécile, tell us what drivers can be actuated to reduce ATB resistance, or AMR. Could you please give us examples of hands-on measures we can implement, whether as individuals or as a group? Thank you, Charlotte. There are 2 dimensions, societal level and individual level. Now, as citizens, there are things we can do every day to reduce ATB resistance because there are different causes. We consume too many antibiotics, we use too many antibiotics, sometimes we misuse them, and we are responsible for that, for what we do as citizens. When we misuse antibiotics, it has an impact. For example, let me think. Say you have a UTI. Usually, all it takes is 1 dose of antibiotics. Or say you have pneumonia, but you don't need to go to hospital, etc. You're not feeling too good. We know it's a bacterial infection. the doctor will give you antibiotics for 5 days. But because it's a beautiful product, just imagine there are 3 doses you need to take per day: morning, lunch, evening. You should start feeling much better after 72 hours. And very often you're thinking, oh, I'm feeling better. I don't need to continue the treatment. So this is something that I experienced in my own family. My father had a pneumococcus-induced pneumonia a year and a half ago. So he was prescribed antibiotics. He's 85 years old, and I reminded him, you got to take your antibiotics. And after 3 days, he told me, no, I went off the treatment because you told me I'm not supposed to generate ATB resistance. So the more antibiotics I take, the more I will generate AMR, so I'll stop it. Okay, Dad, let me explain this to you. Just because you start feeling better after 3 days does mean that your system has completely flushed out the bacteria. No. And if it's 3 times a day, it's 3 times a day, not twice a day. You need to follow the prescription. Because otherwise, the dose of ATBs is not high enough, and this is called a sub-inhibitory concentration, and bacteria love that. This is how they transfer genes. This is how they mutate. And the second thing, if you decide, okay, I'll take it 3 times a day, but only 3 days, not the full 5, no, that's not good, because the bacterial infection is not entirely gone. And if given a chance, it will start multiplying again. So you remember the funnel effect? And the bacteria that are left behind may be extremely tough, much more resistant. So as citizens, please follow the doctor's orders. If you receive a prescription, follow the prescription, of course, assuming that it's substantiated. And don't ask for antibiotics every single chance you get. Very often, patients self-medicate. Oh, maybe you're feeling tired. You're tired of having a runny nose, and if you have a pharyngitis, you may have a fever for maybe 10 days. Have a little fever, and your sputum is green and ugly. It's okay, but that doesn't mean you need antibiotics. But people want to go to work. They're tired of feeling sick. They've had it. They've been feeling like crap for 5 days, and they demand antibiotics. Or maybe you'll take your child to the doctor's office because you haven't slept a wink in 5 days because the kid's crying, and you demand that the doctor prescribe antibiotics. So as citizens, show moderation. Do not make it worse. Do not demand antibiotics. There are things you need to know first.
So respect the doctor's orders. Don't take antibiotics if you don't need to. And then in terms of transmission, well, wash your hands before leaving the bathroom. Wash your hands before you eat. Use a single-use Kleenex when you blow your nose. Wash your hands after you blow your nose. Do not sneeze on your neighbor or in the metro without sneezing into your elbow. So very simple rules. And then at collective level, there's a much more political level that I wasn't really aware of just a few years ago. And then, as was said in the introduction, I'm in charge of coordinating European projects, but not research in public health at European level, to ensure that countries can implement action plans. That now countries, this is what's shown here. So there's the European Commission, which drafted an action plan for Europe to fight against AMR that used to be written by the WHO for world level, and then international organizations, FAO, WHO, the World Animal Health Organization, and then the UN Environment Program, and then now there's a four-party approach. There's also the OECD. And then antibiotic resistance always has to be taken into account during the G7, G20 meetings, so at political level. And without realizing what these projects were at the European policy level, I wasn't aware of the weight of policy in decisions made by us on the ground. And if it doesn't come from the top, it won't go down to the bottom. So it's very important that stakeholders, politics, lobby in favor of keeping antimicrobial resistance as part of the political agenda. And then the largest levers are to monitor the situation, to monitor use of antibiotics, to monitor AMR, and then at national and European level, to also monitor, to have an integrated monitoring mechanism, so for humans, animals, and the environment. Educate people on how to properly use antibiotics, how to prevent infection, so basic things like hand washing. Research, which needs to be funded, including fundamental research, to try to understand all of these complex mechanisms. Raise awareness, inform the public, continue communicating on the topic. And there's a little symbol that we wear very proudly with Christophe. And maybe in October you wear the little pink October ribbon. Well, this is to, and also for breast cancer awareness, but also on the 18th of November, the whole week is devoted to the proper use of antibiotics. And this is the symbol of the fighting against antimicrobial resistance. We're very proud of this. Because it was just recently worn by the Director General of the WHO and a person in the UK. So it was somebody who, so in presence of Prince William. So the next challenge is to have Prince William actually wear the pin. And then we can go onto social media and show how important it is. But no, I'm just kidding. But we need to raise awareness, we need to explain the mechanisms, and we have to keep it high on the political agenda. And this works. I'm sure you all know the campaign that antibiotics aren't automatic. The goal was to reduce consumption by 25%, and it worked. But unfortunately, now it's on the rise again. In medical school, this was a campaign that was in 2001, so a lot of actually the medical students weren't even born. And so when I ask them what the slogan is, they say, well, okay, antibiotics aren't automatic, even though they weren't even born. And so they can say, well, what was the next one? And nobody remembers that one. And you probably don't remember either. We can talk about this later about why. But when the information is solid, then it works. Thank you, Marie-Cécile. We're coming to the last question. So we've seen that antimicrobial resistance, what should be the priority research actions at national, European, and international levels? Well, international level, I talked about this four-party approach before there was the UNEP wasn't part of it before, but there was they introduced the Global Action Plan on Antimicrobial Resistance, and then this was supposed to be translated into national prevention plans with a One Health approach. And all of these national action plans had to take into account a strategic research agenda. So this is currently being developed, not everywhere, because there aren't national plans in every country, and even when there are, they're not necessarily funded, or it's difficult to find funding. So there are strategic research agendas translated at European level. There's the GPIMR program in Europe. It's now in its last year. And the European Commission has now set up partnerships on animal health, animal well-being. This includes antimicrobial resistance, and the one on One Health AMR. So this is a little bit with antifungals, but they're now currently developing their own strategic research agenda. And then you have the main themes, so transmission, intervention, behavior change. So introducing human and social sciences into the research here. This is essential, even if it's not always easy. Everything which is policy interventions, and then cross-cutting endeavors to not forget to study gender, vulnerability. It has been demonstrated that in some African countries, kids taking care of herds, or women taking care of herds mostly, so a few goats, and for cultural reasons, or for practical reasons, they don't go to the vet when there's a problem. And this also leads to issues. So it's the most vulnerable populations which have to be educated there. That's also very important. And at the level of France, we're trying to get structured. I hope you know the Promise plan that was set up a few years ago. So the Ministry of Education and Higher Research provided 40 million euros to research antimicrobial resistance with research projects with budgets of several million euros, and then some structuring projects, one on omega data, another on human and social sciences, and then another that we are co-coordinating, which is called Promise. So it's amr-promise.fr. So here the map of France with all of the institutions represented. So these are structural interventions. The idea being, okay, if we want one health approach, well, first of all, we have to communicate amongst ourselves. For that, we have to get to know each other, and for that, we have to meet. So it's a meeting place, this Promise. It's a meeting club to work on the AMR from a One Health approach. So it's a network for human health, animal health, and then environmental health. So we've emerged through Promise, a network that Christophe mentioned earlier, which is called AMR-ENV. Christophe co-coordinates with Didier Oquet in Besançon. And here we have 25, I think, research units, about 20 research units, all working individually on AMR. And we have them meet to talk to each other, talk about shared indicators. And Christophe could say more about this during the Q&A session. But we really tried to provide structure. And we try to do this as well at the European level through UGMI, which is also monitors with a One Health approach. And we are currently translating this at European level. So I talked about the ERS net for resistance in humans, and we have the ERS VET to monitor resistance in diseased animals, including pets. And we also, over the 4 years at European level, we want to develop ERS ENV, so for monitoring AMR in the environment. Thank you very much for all of these explanations. And I think we'll be able to open the debate and take some questions from people in the room. Hello. Thank you very much for all of these very interesting explanations. I have a question about agriculture. You haven't spoken much about livestock. You say that biocides and heavy metals exert selective pressure. And so when I think heavy metals, I immediately think of pesticides massively used in agriculture. So I very quickly calculated, I mean, it will need to be revised, but just the quantity of antibiotics delivered to people. These are hundreds of tons in France over a year. And pesticides used in agriculture, non-organic agriculture, these are tens of thousands of tons, so 100 times more. So my question is, maybe there's an elephant in the room? All of this poison that we're spreading in the environment, maybe it's a more diffuse selective pressure, but it's probably much higher. And doesn't this maybe have a cumulative effect as well that's under the radar? Is this a hypothesis that has been tested? Is this something that might be plausible? I'll try to answer that. So for antibiotics in the soil, this is studied quite a lot in France. INRIA has examined the question. But then let me remind you of the first the diagram that I showed on the microbiology of the soil. If you think that it's balanced at first, and then you take pesticides or sludge into account, manure, you have an impact on the ecosystem. What we were interested in was to see what type of impact this had. Does it kill the bacteria? Does it modify the ecosystems? And to what levels? So I'm not going to talk about pesticides Well, this is an additional agent that adds to the selection pressure. So, or for example, spreading sludge or manure. So at classical concentrations after being treated to see if this also had an impact on the microflora in the soil. After 3 years of measuring, we didn't find any modification of the ecosystems and no increase in resistant bacteria. So then we added some antibiotics to cheat with our sludge. And if you multiply the dosage of antibiotics by 5 or by 10, you start seeing an effect. So we went to our colleagues from INRIA. They studied this over 10 years, spreading manure on the ground and sludge without seeing any risk. So any develop of specific resistance, which is very positive. But what's important to remember is when you're studying risk, it's not because you can't prove that there's a risk that there isn't one. And it's not because we didn't have COVID that wasn't a risk until it became one. So resistance it's important to see if things have an impact in what you add to the microflora in the soil, but things are much more complex than what people believe. So you need long-term studies, because this is the optimistic view. But then manure, so that comes straight out of the animal, but that isn't treated. Here there's a higher risks. If your animals are taking antibiotics, there's a higher risk. So it's also important to reduce the amounts of drugs given to animals by veterinarians. The overall impact of pesticides on the ground, I'm sure you have the answers since you're asking the question. This is something that we're trying to regulate, but it's underway. I hope I answered. Did we answer your question? Good. So on biocides, a lot are also thrown out with the wastewater from hospitals. A lot of biocides are used. And this is why there's also more and more. So people don't do it for purposes of AMR, but more for sustainable development. So they cleaning much more with water at the hospital, the mother and child hospital, and my hospital. Cleaning is only used with water and microfibers. We no longer use biocides. And Christophe, who takes samples in the wastewater from the hospital, finds a lot of it, and especially like wipes that are also that have biocides. It's not, unfortunately, it's not just in agriculture. But the highest resistances we've found actually has nothing to do with antibiotics. So if you don't take antibiotics, but you still may have resistance to antibiotics even if you're not taking antibiotics. I think there was another question. Yes, hello. Earlier, in terms of statistics, you talked about deaths directly due to AMR and then deaths associated with AMR. What do you mean by that? Well, this is where it gets complicated. I'll try to be understandable. It's the example that I gave earlier. So you're not going to say that your neighbor died of AMR. Let's take the case of pneumonia. You can have pneumonia with a resistant bacteria, and the bacteria resists everything, so you won't be able to find an antibiotic that works. So the person's going to die, and that will be directly attributed to the AMR. But you died of pneumonia. And for X or Y reasons, their condition gets worse. And it's also a resistant bacteria, so things will get worse. The person will probably die. But the fact that it was a resistant bacteria made worse the factor that led to the death. So I'm not sure I made much sense there. It's just a worsening factor and not the causing factor. But it's very complex. There are different methodologies. And if you look at a European study on the number of deaths in France yearly, and then one by the French health authorities, who said 5,000 deaths linked to AMR in France, but the Europeans said 33,000 for Europe, and I think 12,000 for France, so 5,000 to 12,000, depending on the methodology of the epidemiologists. Hello. To come back to what was said about some infections which are harder and harder to treat because of AMR, we often hear about bacteriophagi. Is this something that might work? Does this have a future? Can it be widely used? If you had asked me the question 10 years ago, I would have said, well, yeah, I don't know. These are viruses, so viruses of bacteria. I thought, ooh, what's this? What's going to be like this long-term integrated into the genome? But what we see today is that we have very few new antibiotics, very few industries investing in new antibiotics. That's another topic, but it's an economic topic, which can have a major impact because there is no return on investment because the economic rules are the same for antibiotics as for other drugs. But that's a model that has to change. There are a lot of people working in this area to try to find economic motivations. So the pull incentives so that the industrials start looking for new antibiotics. Again, it costs millions and millions of dollars, and it might work once. But then as microbiologists and clinicians, we say, wait, don't prescribe this too much because we don't want to develop new resistance. So we have to change the model. For these viruses, well, there are more and more studies that show, well, there's a team in Lyon that works on this, Frédéric Laurent and Tristan Ferré. So it's more and more used for serious infections locally. So diabetics or articulations. And there are more and more studies about using them systemically. And this is also used in veterinary medicine. But for either humans or animals, the trouble is regulation. Right now, there is no regulation around using these bacterial eating fungi. Viruses. And we started a work stream on antibiotics at European level. And the fact that there's no right way of using them. So we give molecules of very broad spectrum molecules because we no longer produce penicillin. And then in low and medium income countries, well, they would want to have antibiotics, but they don't. And that's why the policy level is important. And within the UGMI, in the work package on antimicrobial resistance, they want to think specifically about these viruses. And last week or 10 days ago, the WHO had a webinar on that technology, and I believe it's still accessible online. And so for what infections, how, I mean, all of this remains to be defined, but do have a look. And there are companies in France, one that is working on this. Thank you. And we also have a few questions online. So earlier, you talked about factors to do, well, you talked about the transmission hotspots where bacteria found their way into the environment. So thinking about hospitals and their contribution of 80% of all bacteria with antibiotic resistance. Are there regulations planned or studies underway Sorry, I'm trying to find a way to put this. So to regulate the amount of antibiotics, the concentrations of antibiotics in the wastewater from hospitals. No, so far there is no regulation. It's monitoring. I think there are 2 molecules that are monitored at European level. No, there are about a dozen, 5 or 7. But they're only monitored. And these are also drugs, they're not antibiotics. So antibiotics, I think it's 2 or 3. What the trouble with the hospitals, though, is complex. And the first question was, should we treat the wastewater from hospitals being a source of AMR? And so if we process this water, then this will help solve the problem upstream. But actually, it was a false good idea, because what we realized is that most of the bacteria came through the urban wastewater, because the two, and then actually to be profitable, it was much better to have a municipal wastewater treatment plant to treat everything. So this was a 5-year study, and there was a hospital that was built at the same time as a wastewater treatment plant. And the prefect said, no, we cannot mix these 2 flows until we can prove that the wastewater can be treated. But people realized that it was much better to actually to treat the wastewater. But all these questions are very important, because there are other countries that have made different decisions. For example, hospitals that have pre-treatments for their water at the hospital directly to try to minimize the load. So they treat everything, so for drugs and bacteria. And then the question is also financial. Who will pay if the hospital is going to treat their own water? Would it be citizens, or would it be the hospital's budget? So a lot of things to be set up, but people are thinking about trading wastewater directly from hospitals. So a question online: what type of disinfection is the most useful to reduce AMR? Well, I'm not in charge of designing disinfection stations. So there are membranes that can be used to remove matter from the water. But it all depends on what you want to do with the water afterwards. If you want to completely disinfect water, well, then you have to disinfect it. And this will be very intrusive. You'll have to add chemicals, and it will be corrosive to really disinfect the water. And is this something that the treatment plants should do? And then there's a question of reuse. Is it reused for drinking, or reused to be used in other processes? What's currently being developed are using membranes. And that's a compromise between very effective in reducing the bacterial load and effectiveness. But then you can also... but there are a number of procedures for disinfecting, but it all depends on what you want to use the water for. Thank you. So another one. So among the main causes of the development of AMR, do we know if any contribute much more than others? Antibiotics consumed by humans, by animals, due to pesticides, etc. It's complicated. It's complicated because you can't dissociate that from transmission, as I said earlier. We know, for example, there are some classes of antibiotics which have a power of selection or on the mutation. Not long ago, there was a recommendation by the High Health Authority to reduce the use of fluoroquinolones. So that's no longer recommended as a first treatment for low-level pathologies. But these are molecules that used to be used very widely. If I could just add to this, this is a molecule that was also found a lot in the environment because they stay stable, contrary to penicillin, which you don't find in the environment. So that was a double effect. So there's a role in selection pressure, but then it's more complicated than that because fluoroquinolones also play a role. So I just only talked about selection pressure, but there are also molecular mechanisms at a very small level. It's incredible what these tiny little bacteria that you can't see. It's amazing what they can do. And this can also trigger genetic systems which allow the bacteria, when they're in the presence of certain antibiotics, they trigger an SOS response, which can trigger a whole bunch of other things, that it will mutate more and do other things. And some of these other things are to express resistance genes or accelerate the transmission of genes to get resistance genes from others, which, okay, they don't do it on purpose, but this is what they do. So they increase the chances of acquiring resistance genes. And once they get the right one that will allow them to resist the antibiotic selection pressure, well, then it's much easier for them. So not all molecules have the same impact. Heavy metals, for example. So in all our little Russian dolls, sometimes the same genetic material, a resistance gene will be alongside an antibacterial resistance gene, which will be right beside a heavy metal resistance gene. And so when those are transferred from one bacteria to another, well, then maybe you have a UTI due to a resistant bacteria because they're resistant to this bacteria, this antibiotic, but maybe they're also resistant to heavy metals, but that you don't know. So one last question from the room. So coming back to the question on the most effective procedures for water treatment. We didn't talk a lot about sludge. And I was wondering if there are studies underway on the accumulation of AMR in sludge. And do we know if the ways of treating sludge or processing it is a way of also monitoring that risk potential? Because I also thought in terms of risks for soil health, right now we're quite optimistic.
I don't know whether we truly are optimistic, but I think that some rivers all concerns regarding some rivers are less than what we used to feel. So we've been working on resistance in soils. We have 2 teams, plus 1 team from the INRAE Institute, because the matrix is complicated. So there are lots of difficulties. But just because it's difficult doesn't mean we're not doing it. We try. We try to work on it. And as it happens, yes, we do find levels of resistance in sludge, but the concentrations are very different. Now, the CPBEL study that we talked about before, we looked at mixed sludge, mixing wastewater and sludge from urban environments and also hospitals. And it's true that hospital sludge has much higher concentrations. I'm not saying that is more dangerous, but there's a so-called genetic signature of ARGs that is slightly different. And the next phase are the risks. Well, yes, there are. Obviously, hospital sludge, we're not going to take a chance and spread it on fields as fertilizers, but mixed sludge, well, the signature profile isn't that different because of the dilution. Now, there was no prior disinfection. We didn't use lime for disinfection. Lawmakers decided that the risk was low and was therefore fit for use as fertilizers. And at the end of the day, we decided to burn the sludge. It was close to the border with Switzerland, so we didn't want to take a chance. So what did you do with the sludge? That's the question. So you need to take action when it comes to the soil. We know that the soil is going to reduce the bacterial load. It's one of the bonuses. And know that in France we believe in using sludge as fertilizers for fields, but we believe that the transfer of ARGs does not necessarily demonstrate any resulting activity. We are unable to demonstrate specific gene transfers that would have to do with environmental bacteria that would capture genes from bacteria that come from processing plants. But if you move into metagenomics, you're starting to see movement, but it's much more complex to interpret, much more difficult to determine the mechanism. But we've got teams working on this. Reuse, in particular, has revived the problem. And because of COVID, we're doing a lot more work now on sludge and gene transfers. And there's a lot to explore there. Thank you. Thank you so much. Time's up. Thank you so much to our two speakers, Marie-Cécile and Christophe. Please answer the satisfaction questionnaire and join us for a buffet lunch. We will continue this conversation. Thank you very much.